Hi friends, in today's video we want to talk about the directional derivative. Now the directional derivative is something that's very important to multivariable calculus. It's probably one of the more general things that we cover in the course. So this is the most general form of the partial derivative, or the derivative that actually makes sense for us. So essentially what the directional derivative says is it says, hey, I can find my partial derivative with respect to x. I can find my partial derivative with respect to y. But x and y are just two directions that we can have, right? So if I'm finding the partial derivative with respect to x, I'm finding the derivative along this line. If I'm finding it with respect to y, I'm finding it along this line. But what if I want to find it along this line, or any other line that passes through the origin of our point where we start? Well, the directional derivative tells us how to find the derivative of a multivariable function in the direction of some unit vector. Any unit vector. It doesn't need to just be I hat or j hat. It could be any unit vector, which we'll call u hat. So we'll determine how to deal with that in today's video. So something very important. So we'll get started right now. So directional differentiation takes the idea to find the derivative of a two-variable function. It can be more than two. We'll cover that generalization later. Find the derivative of f of x and y at x naught, y naught in the direction of u hat. And u hat can be broken down into components of a and b. Okay, so we are finding the derivative in the direction of a unit vector. Now, the way that we do that is, if I want to do that, I'm perturbing my x now, and I'm perturbing my y. So I'm perturbing x and y in my little limit to find how my function changes. So we change it based on components, and h will be modified by whatever components we have. So the directional derivative in the direction of u at f of x naught, y naught is equal to the limit as h approaches 0 of f of x naught plus ha, comma y naught plus hb minus f of x naught and y naught over h. This is a very similar definition. Now we can see that in the case where if u equals 1, 0, and this is equal to I hat, or j hat equals u equals 0, 1, well, these are the unit vectors for x and y. So if I take the directional derivative on I hat of f, that's equal to partial f partial x. And if I take the directional derivative along j hat of f, then that's equal to partial f partial y. So this reduces to our general case for the partial derivatives. So what we can do is we can actually say that the directional derivative of f of x and y in the direction of u is equal to partial f partial x times a hat, or times a component, plus partial f partial y times b component. And we can rewrite this if we know the direction, or if we know the angle between the vector, and we know it's a unit vector, so we don't have any magnitude, or magnitude is 1. We can get partial f partial x cos theta plus partial f partial y sine theta. Now let's say we want to generalize this. So we have a function of n variables, so f of x1 all the way to xn, and then u hat is defined with components a1 all the way up to an. Then we can define the directional derivative in the direction of u of f as being equal to the sum of partial derivative of f with respect to the ith variable times the ith component of the unit vector. So in the two-variable case, that's partial f partial x times a sub 1 plus partial f partial y times b, right? Okay, so why don't we try an example with this? So this graph down here is just the directional derivative that we're going to be trying to find, or it's a function whose directional derivative we're trying to find in a specific case. Find the directional derivative in the direction of u for f of x, y, if f of x, y is equal to x cubed minus 3xy plus 4y squared for some theta equals pi over 6. Okay, so this is the case in which we are dealing with an angle and not the components of the unit vector. So to do this, we will plug it into our formula. So the partial derivative, or the directional derivative in the direction of u for this function is equal to partial f partial x cosine pi over 6 plus partial f partial y sine pi over 6. So what we do is we can find those cosine and sine values and find our partial derivatives of this function, which is easy enough because this is just a polynomial. And what we get is 3x squared minus 3y times root 3 over 2 plus negative 3x minus 8y over 2, which is equal to 1/2 3 root 3x squared minus 3x plus 8y minus 3 root 3y. Okay, so now let's say I want to find the directional derivative, the direction of u of function f at 1, 2. Well then, I just plug in 1 and 2 for my x and y values, and I get 13 minus 3 root 3 over 2. So that's the main idea behind the directional derivative. It's not super complicated, it's just bringing back some of the vectors and 3D space ideas from 2 units ago. That's just fairly important for us to remember. Alright, in the next video we are going to introduce the gradient. The gradient is a super important topic in multivariable calculus. It's probably one of the most important topics that we learn this unit, so we'll get into that in the next video. We'll see you then. Thanks for watching.